The night sky holds a secret invisible to our eyes. If you could see the universe in X-ray vision, the familiar constellations would vanish, replaced by a ghostly, all-encompassing fog. This is the cosmic X-ray background, a faint high-energy glow coming from every direction in space. Astronomers have been trying to crack this code for over half a century. We are about to unravel its 25 biggest mysteries, a cosmic detective story spanning the entire history of the universe. By the end, you will understand what this pervasive glow reveals about the most violent forces in existence, from hidden black holes to the missing atoms of creation. What is creating this eternal, high-energy shimmer, and what can it tell us about the fate of the cosmos itself? What is the most profound secret you think the universe is still keeping from us? The year was 1962, and a small team of scientists led by Riccardo Giacconi was preparing for a brief rocket flight. Their goal was simple, or so they thought. They aimed their Geiger counter at the moon, hoping to detect X-rays bouncing off its surface from the sun. For a few precious minutes above the atmosphere, their instrument scanned the darkness. But the data that came back was not a signal from the moon. It was something far stranger, a steady and powerful hiss of X-rays coming from every direction, a uniform glow that painted the entire sky. The initial confusion was profound. This was not a single bright object, it was a background, a pervasive fog of high energy that no one had predicted. In that single moment, our understanding of the universe was fundamentally rewritten. A major, invisible component of reality had just announced itself. This was not merely a new set of objects to catalog, it was an entirely new layer of the cosmos, a hidden dimension of violent energy that had been there all along, waiting for us to develop the eyes to see it. What other fundamental pieces of our reality are we still blind to, simply because we haven't yet built the right tool to perceive them? That initial discovery presented a puzzle far deeper than anyone had anticipated. Why was this X-ray glow so incredibly smooth? It wasn't a collection of distinct, sharp points of light, like stars in the night sky. Instead, it was a uniform, ethereal fog, a seamless veil draped across the entire cosmos. If the source were nearby objects within our own galaxy, you would expect a lumpy, uneven distribution concentrated along the plane of the Milky Way. But this was different. This was a perfect, almost featureless canvas. This profound smoothness ruled out any simple, local explanation. It meant the X-rays weren't coming from a stellar neighborhood close to home. They had to be coming from sources so incredibly far away and so numerous that their individual points of light had blurred together into a single, uniform glow, just like the individual trees in a vast forest blend into a single shade of green when viewed from a great distance. This was the first major clue that the cosmic X-ray background was a truly cosmological phenomenon, a relic woven into the very fabric of the universe itself. Its perfect smoothness became the first and most important rule for any theory trying to explain it. Whatever was creating this energy had to be ancient, widespread, and exist in such staggering numbers that from our vantage point, they painted the entire sky without a single brushstroke showing through. How could anything in the universe be so uniformly violent and yet so perfectly hidden in plain sight? The hunt for the source of this cosmic fog began with the most obvious culprits, the universe's most powerful natural engines of destruction. Astronomers turned their gaze to the hearts of distant galaxies, where supermassive black holes, containing the mass of millions or even billions of suns, lie in wait. When these monsters feed, they do not do so quietly. Vast whirlpools of gas and dust, called accretion disks, spiral inward at near light speed. Friction heats this material to unimaginable temperatures, millions of degrees, causing it to shine with a ferocious intensity across the entire electromagnetic spectrum, but especially in X-rays. These feeding frenzies are known as active galactic nuclei, or AN, and they are among the brightest steady sources of energy in the entire cosmos. A single one can outshine every star in its host galaxy combined. With such raw power, they seemed like the perfect solution. If you had enough of these brilliant beacons scattered far enough across the universe, their combined, blurred light could easily create the smooth, all-pervasive X-ray glow we detect. It was an elegant and compelling answer. The case, it seemed, was almost closed, but was this explanation too perfect? Could these brilliant, violent monsters truly be the only artists responsible for painting the entire sky with their energy? But the elegant solution began to crumble under closer scrutiny. As our X-ray telescopes grew more powerful, they started to pick out individual points of light from within the cosmic fog. Astronomers began to carefully count these bright AGN, expecting their numbers to finally add up to the total glow. The math, however, produced a shocking result. There was a glaring deficit. The combined light from all these brilliant, feeding black holes fell dramatically short. It was like trying to fill an ocean with the water from a few dozen Great Lakes. The sheer scale of the mismatch was baffling. This became known as the log and log S problem, a technical name for a very simple but profound puzzle. The number of bright sources we could see, labeled N, and their brightness, labeled S, just did not follow the pattern you would expect if they were the sole contributors. The curve was all wrong. The universe was presenting us with a bill for an immense amount of energy, but the obvious suspects we had in custody could not cover the cost. This forced a revolutionary and almost unsettling idea into the spotlight. The universe had to be teeming with a hidden population of active galaxies, a silent majority we had completely missed. These couldn't be the brilliant, obvious beacons we already knew. They had to be fainter, shrouded in cosmic dust and gas, their fierce X-ray light muffled before it could ever reach our telescopes. We were not just missing a few black holes, we were missing an entire class of cosmic phenomena, a ghostly legion operating in the shadows. How do you begin to hunt for monsters that have mastered the art of invisibility? The hunt for these hidden monsters required a new kind of eye, one with vision sharp enough to see through the cosmic fog. That eye arrived in the summer of 1999, when the Space Shuttle Columbia carried NASA Chandra X-ray Observatory into orbit. Named after the Nobel Prize-winning astrophysicist Subramanian Chandrasekhar, this was not just another telescope, it was a revolution in high-energy vision. Chandra's most powerful gift was its incredible angular resolution. Think of it this way: if you were standing in New York City, Chandra could read a stop sign from a distance of 12 miles away. This phenomenal sharpness meant it could finally do what no instrument had ever managed before. It could stare into the heart of the X-ray fog and pick out the individual pinpricks of light that were blended together to create it. And that is precisely what it did. When Chandra turned its gaze to a seemingly blank patch of sky and stared for weeks, it didn't see a uniform glow. It saw a spectacular firework display, millions upon millions of individual point sources, each one a tiny, brilliant spark against the darkness. The cosmic background was not a smooth, fundamental energy at all. It was a crowd, a vast metropolis of individual objects. This was the final, definitive proof that the theorists were right. The universe was indeed filled with a hidden population of active galaxies. Chandra's census confirmed that a huge fraction of the background glow came directly from these feeding black holes, finally putting numbers to the ghostly legion. But in solving one mystery, it deepened another. Even with millions of AGN now accounted for, a portion of the background remained stubbornly diffuse, a true fog that refused to be broken down. So what were the other artists, the ones whose light was so faint or so thoroughly smeared that not even Chandra's sharp eyes could pick them out. So the universe was playing a cosmic game of hide and seek, and the hidden black holes had found the perfect cloaking device. They are known as obscured active galactic nuclei, and their secret lies in a shroud of cosmic debris. Picture a brilliant lighthouse, its powerful beam cutting through the night. Now imagine a thick, dense fog rolling in, swallowing the light until only a faint, muffled glow remains. This is precisely what happens around these hidden monsters. A supermassive black hole at the center of a galaxy is surrounded by a colossal donut-shaped structure of gas and dust, trillions of miles across. When the black hole feeds and unleashes its torrent of X-rays, that energy must first pass through this shroud. The lower energy X-rays are easily absorbed and blocked by the thick clouds, while only the most powerful, high-energy X-rays can punch through. To our telescopes, this doesn't look like a brilliant beacon. It looks like a dim, faded ghost, or sometimes nothing at all. The most extreme of these are called Compton thick active galactic nuclei, named for the physicist Arthur Compton, who described how X-rays scatter in such environments. Their shrouds are so incredibly dense, it is like trying to see a light bulb through a concrete wall. We know they are there because we can see the indirect evidence, the shadow they cast on the surrounding gas, or the faint, high-energy whisper that just barely escapes. But directly detecting them remains one of the greatest challenges in X-ray astronomy. This hidden majority, these muffled monsters, are now believed to make up a huge portion of the active black holes in the universe. They are the silent workforce, contributing a massive amount of energy to the cosmic background glow, while remaining almost completely invisible to our direct gaze. How many more of these cloaked giants are lurking in the darkness, their violent hearts beating silently behind impenetrable veils of dust and gas? This cosmic feeding frenzy, captured in the X-ray glow, gives us something extraordinary. It is a fossil record of black hole growth. The energy we detect, spread so evenly across the sky, is not just random noise. It is the sum total of every meal consumed by supermassive black holes across nearly the entire lifetime of the universe. Think of it as a cosmic ledger, a detailed energy budget that has been meticulously kept for billions of years. Every X-ray photon in that background represents a tiny amount of mass falling into a gravitational abyss, its potential energy converted into a brilliant, high-energy flash before being forever lost. By measuring the total intensity of the X-ray background, astronomers can essentially add up all this energy. They can calculate the total mass that must have been devoured to produce it. The answer is staggering. To power the glow we see, supermassive black holes collectively had to consume an amount of gas and stars equivalent to the mass of tens of millions of suns every single year for billions of years. This is how we know that the quiet, dormant giants we see in galaxies today, including the one at the heart of our own Milky Way, were once ravenous titans in their youth. The cosmic X-ray background is the echo of their primeval feasts, the lingering heat from a time when the universe was a far more violent and chaotic dining hall. So we are not just mapping light, we are weighing the entire growth history of the most massive objects in existence. What does this ancient dinner menu tell us about how these monsters were born, and what finally forced them to push away from the table? But the story of the cosmic X-ray background is not written by black holes alone. As astronomers tallied the energy from these hidden monsters, they realized a portion of the glow remained stubbornly unaccounted for, pointing to another, even more elusive contributor. This leads us to one of cosmology's greatest mysteries, the case of the missing baryons. Baryons are simply the particles that make up all the ordinary matter we know and love, the protons and neutrons that form every atom in every star, planet, and person. Based on our most precise measurements of the early universe, We know exactly how much of this ordinary matter should exist today, yet when we add up everything we can see, all the stars and galaxies and cool gas clouds, we come up dramatically short. Nearly half of all the atoms that should be here are simply gone. It is as if someone removed every other atom from the cosmos. Where did they go? The leading theory is that these missing baryons are not gathered in neat, visible structures. Instead, they are spread out in a vast, diffuse web of incredibly hot gas that fills the immense voids between galaxies. Think of this as the universe's true atmosphere, a thin, searing soup of matter that has been heated by the shock waves of cosmic formation to temperatures of millions of degrees. And gas that hot does something very specific. It glows in X-rays. This faint, pervasive emission from the warm, hot intergalactic medium, as it's formally known, is believed to weave its own subtle thread into the fabric of the cosmic X-ray background. It is the ghostly signature of the universe's hidden skeleton, the whisper of atoms that are lost to our eyes but found by their heat. So when we look at that faint, all-sky glow, we are not just seeing the violence of black holes. We might also be staring directly at the answer to a cosmic census problem, finally spotting the invisible ocean of ordinary matter in which all galaxies merely float. What other fundamental truths are written in this faint, high-energy light, waiting for us to learn how to read them? This warm, hot intergalactic medium, this cosmic scaffolding, is a ghost on an epic scale. Its structure is not solid but a delicate tracery of filaments, a spiderweb woven on the grandest possible loom, connecting entire clusters of galaxies across billions of light years. The gas within these filaments is so incredibly thin, a near-perfect vacuum by earthly standards, with perhaps only a single atom in a space the size of a typical office room. Yet these atoms have been superheated by the violent birth pangs of the universe itself, by shockwaves from exploding stars and the relentless pull of gravity, reaching temperatures of hundreds of thousands, even millions of degrees. A gas that hot does not glow in visible light. It emits a faint, specific signature of X-ray photons. This is the tantalizing promise, the reason astronomers look so closely at the cosmic X-ray background. They believe this faint, all-sky glow holds within it the cumulative whisper of this entire hidden structure, the combined X-ray emission from every single one of these ultralight, ultra-hot filaments. Isolating that specific whisper, however, is like trying to hear a single conversation in a stadium filled with a roaring crowd. The signal from the warm, hot intergalactic medium is staggeringly weak, completely drowned out by the combined roar of millions of active black holes and other bright X-ray sources. Our current telescopes simply lack the sensitivity to map this faint emission directly. The hunt, therefore, relies on clever, indirect methods. Astronomers search for the shadows this gas casts. When the light from a brilliant, distant quasar passes through one of these filaments on its long journey to Earth, the superheated gas can absorb specific, very high-energy X-rays from the quasar's beam. By analyzing the resulting dimming, scientists can infer the presence and properties of the invisible filament. Each successful detection is a triumph, a single thread pulled from the cosmic tapestry. But to confirm that this web is a major contributor to the X-ray background, we need to find not just one thread, but the entire weave. This is the profound frustration and the exhilarating potential of this mystery. The answer to where half the universe's ordinary matter has been hiding might be shining softly in a light we have already detected, a secret waiting within a secret, just beyond our current ability to fully unravel. While the warm, hot intergalactic medium forms a delicate cosmic web, there are places where this invisible matter gathers into colossal, lumpy knots of pure violence. These are the galaxy clusters, the largest gravitationally bound structures in the entire universe. Each cluster can contain thousands of galaxies, all swarming like bees around a hive, but the true monster is not the galaxies themselves. It is the space between them. Trapped by the cluster's immense collective gravity is a vast ocean of superheated plasma known as the intracluster medium. This is not a thin, wispy gas. It is a seething, roiling sea of matter, so incredibly hot that it reaches temperatures of tens of millions of degrees. At such extremes, the atoms are torn apart, electrons are stripped from their nuclei, creating a soup of free particles moving at tremendous speeds. When these particles collide, they release a torrent of high-energy photons, and this emission peaks squarely in the X-ray part of the spectrum. A single galaxy cluster does not just glow in X-rays, it shines with the ferocious intensity of a billion suns, outshining the combined light of every star in every galaxy within it. This makes these clusters brilliant, unmistakable beacons in the X-ray sky, but their contribution to the cosmic background is not a smooth, uniform one. Because clusters are not evenly spread throughout space, they form at the dense intersections of the cosmic web, creating a lumpy, patchy distribution across the heavens. When we look at the overall X-ray glow, this lumpiness adds a specific texture. It is a component of the background that is not perfectly smooth like the blended light of distant black holes. Instead, it creates subtle, large-scale variations, a faint modeling of bright spots and dark voids that corresponds to the richest concentrations of matter in the universe. This is the signature of the intracluster medium, a distinct voice in the cosmic choir. Its energy tells us not just about the gas itself, but about the awesome power of gravity to trap and heat matter on the grandest of scales. What other colossal structures, hidden in plain sight, are adding their own unique texture to this eternal, high-energy whisper? Yet even as we map these colossal structures, a different kind of violence is contributing to the X-ray sky, one that plays out on a much more personal, stellar scale. Scattered throughout our own galaxy and every other, the corpses of dead stars are writing their own fiery epilogues in high-energy light. These are the stellar endpoints, the final, dramatic chapters in the lives of stars, and their faint, cumulative glow adds a local veil that astronomers must carefully peel back to see the true cosmic background. The most prominent of these local sources are X-ray binary systems. Picture a cosmic vampire, a neutron star, or a stellar mass black hole locked in a tight, deadly dance with a normal, sun-like companion star. The intense gravity of the dense corpse relentlessly strips material away from its partner. This stolen gas doesn't fall quietly. It spirals inward at a significant fraction of light speed, forming a searingly hot accretion disk around the dead star. The friction within this disk heats the gas to millions of degrees, causing it to shine brilliantly in X-rays. A single one of these systems can outshine the sun by a factor of 100,000 in this part of the spectrum. Then there are the expanding, superheated remnants of supernova explosions. When a massive star dies in a cataclysmic blast, it hurls its outer layers into space at thousands of miles per second. This expanding shell of debris, a supernova remnant, collides with the surrounding interstellar gas, creating a shock wave that heats the material to X-ray emitting temperatures. These glowing nebulous wreaths mark the graves of stars, and they too add their faint signature to the local X-ray foreground. From our vantage point within the Milky Way, this stellar cacophony creates a diffuse, patchy glow that lies between us and the distant cosmic background. It is a foreground noise, the X-ray equivalent of the haze of city lights that obscures our view of the faint, distant stars. To see the true cosmological signal, the echo from the early universe, scientists must first create a detailed map of all these nearby sources and meticulously subtract their combined light. It is a painstaking process of cosmic cleaning, revealing that the grandest mysteries are often hidden behind the brilliant, violent deaths of our stellar neighbors. If every dead star leaves a faint, high-energy whisper, what does the combined murmur of all the stellar ghosts in the universe ultimately tell us about the life cycle of matter itself? Despite our most powerful tools, a stubborn sliver of the cosmic X-ray background refuses to be explained, even after Chandra and other observatories picked apart the fog into millions of individual points of light. A portion of the glow remained truly diffuse, a faint and seamless veil that no telescope could resolve into distinct sources. This is the unresolved fraction, the final frontier of this mystery, and it represents the bleeding edge of our cosmic knowledge. What could possibly be so faint, so uniformly spread, or so deeply hidden that it evades detection by our sharpest instruments? One compelling suspect is the faint, cumulative whisper of the warm, hot intergalactic medium itself. The combined X-ray emission from that vast, searing web of missing atoms, while incredibly weak from any single filament, might add up to a detectable signal when summed across the entire sky. This unresolved glow could be the direct signature of the cosmic scaffolding, the faint but persistent heat of the universe's hidden ocean of ordinary matter. Another tantalizing possibility points to the very edge of time. The first supermassive black holes to form in the universe, known as seed black holes, must have ignited in an era of profound darkness. Their initial feeding frenzies would have been ferocious, but their light has been traveling for so long that the expansion of the universe has stretched their X-rays into an incredibly faint, low-energy hum. This primordial background from the dawn of the first monsters could be blended so thoroughly into the fabric of space that it appears to us as an unresolvable mist. Or perhaps the answer lies in an entire zoo of faint, high redshift sources we have not yet even conceived of, dimmer active galaxies, vast populations of distant stellar corpses, or even exotic, theoretical objects that operate on principles we have yet to discover. This unresolved fraction is more than just a missing piece of a puzzle. It is a direct message from the cosmic unknown, a challenge written in the oldest light. It tells us that our census of the violent universe is still incomplete, that our maps of reality still have blank spaces labeled "Here be dragons." What incredible discoveries are waiting for us, hidden within that faint, uncharted glow? Every single X-ray photon in that cosmic fog carries a hidden signature. The precise energy of each particle of light, from the faintest whisper to the most powerful blast, is not random. It forms a distinct pattern, a unique fingerprint known as the energy spectrum. This spectrum is the master key to the background's origins, and its shape tells a story far more complex than anyone first imagined. Think of it like listening to a vast orchestra. If the cosmic X-ray background were a single, pure note, it would be easy to identify the instrument playing it, but it isn't. It is a rich, layered chord, a symphony of different pitches and tones all playing at once. In X-ray terms, these pitches are described as soft and hard. Soft X-rays are lower energy, like the gentle pluck of a violin string. Hard X-rays are higher energy, more like the powerful blast from a trumpet. The overall shape of the spectrum, the balance between these soft and hard components, acts as a cosmic diagnostic tool. A simple, pristine glow from a single type of source, like unobscured black holes, would produce a very specific, predictable spectral shape, but the real universe is messy. The spectrum we actually measure is a complex tapestry that no single source can reproduce. It has bumps, dips, and a particular slope that defies a simple explanation. This mismatch is a profound clue. It forces us to conclude that the background is not the product of one cosmic phenomenon, but a mixture of many. The hard X-rays likely come from those heavily obscured black holes, the ones shrouded in thick clouds of gas. Their lower energy X-rays are blocked, allowing only the most powerful, penetrating hard X-rays to escape and reach us. Meanwhile, the softer components could be a blend of unobscured black holes, the searing heat of galaxy cluster gas, and perhaps even the faint, warm glow of the missing intergalactic matter. Each type of source, with its own unique temperature and environment, imprints its own signature onto the spectrum. The final shape we see is the sum of all these voices, a layered history of cosmic violence, absorption, and temperature written in a language of light we are only just learning to read. What other secrets are encrypted in the subtle curves of this ancient, high-energy light? This cosmic symphony of X-rays has not always played at the same volume. The universe's violent side has a rhythm, a history of rising crescendos and fading whispers that is written directly into the fabric of the background itself. To read this history, astronomers use a natural time machine, the phenomenon of redshift. Because light takes time to reach us, looking deeper into space is the same as looking further back in time. When we observe the X-ray background originating from a specific redshift, we are effectively tuning into a specific chapter of cosmic history. What these observations reveal is a dramatic story of boom and bust. The universe experienced a golden age of violence, a period often called cosmic noon, that occurred when the cosmos was roughly half its current age. During this epoch, the supermassive black holes at the hearts of galaxies were in a state of frenzied, chaotic feasting. Gas was plentiful, galactic collisions were common, and these gravitational monsters were accreting matter at a ferocious rate. The X-ray sky during cosmic noon would have been a spectacular, blinding tapestry of brilliant active galactic nuclei, far more numerous and energetic than anything we see in our local modern universe. The collective energy output was staggering, and it is this primeval frenzy that contributes a massive portion to the total X-ray glow we measure today. But cosmic noon did not last. The feast eventually turned to famine, as the most accessible gas was consumed or blown away by powerful jets, and as galaxies settled into more stable configurations, the black hole's food supply dwindled. The brilliant beacons began to dim, one by one. The frenetic activity slowly declined, settling into the relatively quiet universe we inhabit today, where only a fraction of black holes are still actively feeding. This evolutionary history is not just a footnote, it is a fundamental part of the X-ray background's identity. The glow we see is not a static snapshot. It is a layered archaeological record, a cumulative sum of all this violent activity across billions of years. The light from cosmic noon is still arriving, mixed with the fainter whispers from earlier and later times. By carefully dissecting the background spectrum and its sources at different redshifts, we have uncovered the life story of the universe's most powerful engines. Their rise and fall shape the cosmos we see, and their fading echo is the gentle, high-energy hum that now permeates all of space. What other rhythms of cosmic life and death are encoded in this ancient, lingering light? The violent energy of these feeding black holes did far more than just leave a glowing echo. It actively shaped the cosmic landscape we see today, forging a profound and unexpected link between the invisible and the visible. The energy captured in the X-ray background was not merely a byproduct of growth, it was a sculptor's tool. This leads to one of the most transformative ideas in modern cosmology, the feedback hypothesis. Picture a supermassive black hole at the center of a young, gas-rich galaxy. It is feasting, unleashing a torrent of radiation and channeling colossal jets of plasma that can travel for millions of light years. At the same time, the galaxy around it is busy forming new stars, condensing that same reservoir of cold gas into stellar nurseries, But here is the cosmic catch. The ferocious energy from the black holes slams into the surrounding galaxy like a hurricane. It heats the cool, star-forming gas, preventing it from collapsing. It drives powerful winds that can blow the galactic gas supply clear out into intergalactic space. In a single, furious act of self-regulation, the black hole effectively shuts off its own food supply and, in the process, halts the birth of new stars in its host galaxy. This is AGN feedback, a cosmic balancing act of breathtaking power. The black hole's growth is intrinsically tied to the growth of its galaxy. It cannot grow too massive, too quickly, without triggering a feedback loop that stifles both its own appetite and the galaxy's ability to create stars. The energy we see in the cosmic X-ray background is the tangible record of this ancient struggle. Every X-ray photon is a relic from an era when black holes and galaxies were locked in a violent dance, each dictating the other's ultimate fate. The brilliant glow we measure is not just the signature of consumption, it is the fossilized evidence of a relationship that determined the size, shape, and stellar population of every giant galaxy we see in the night sky. How many galaxies were forever quieted by the very monsters that gave them shape, but what ignited this cosmic dawn of violence in the first place? To find the ultimate source, we must journey back to the very edge of time, to an era before the first galaxies fully formed. This brings us to the profound mystery of the first black holes. The universe's original monsters could not have been born with the weight of billions of suns. They must have started from seeds, tiny by cosmic standards, and the nature of those seeds is one of the greatest unsolved puzzles in astrophysics. Two leading theories paint dramatically different pictures of this violent birth. The first involves the hypothetical population, 3 stars. These were not like the stars of today. They were behemoths, pure hydrogen and helium giants that could have been hundreds of times more massive than our Sun. Their lives would have been spectacularly brief and violent, ending in colossal supernova that left behind black hole seeds with masses perhaps a few dozen times that of our Sun. The other, more exotic possibility is the direct collapse black hole. In this scenario, vast clouds of primordial gas could have collapsed under their own gravity so rapidly and catastrophically that they skipped the star-forming stage entirely, punching a hole directly in the fabric of spacetime to create a seed black hole with a mass 10,000 times that of the Sun or more from the very first moment. These two paths lead to profoundly different infant universes. One is a cosmos lit by the brief, brilliant lives of unimaginable stars. The other is a darkness punctuated by the sudden, silent appearance of ready-made gravitational pits. Both of these primeval objects would have fed voraciously on the pristine gas around them, glowing fiercely in X-rays. Their light, however, has been traveling for so long that the expansion of the universe has stretched it, redshifted it into an incredibly faint, low-energy hum. This is the tantalizing possibility, the unresolved portion of the cosmic X-ray background, that final, diffuse veil that refuses to be broken down, might not be an artifact or a flaw in our data. It could be the collective, faded whisper of these first seeds. It might be the fossilized light from the universe's very first feeding frenzies, a background within the background, a signal from the birthplace of all supermassive black holes that has been smoothed into a nearly imperceptible mist by 13 billion years of cosmic expansion. We are therefore listening for the echo of creation itself, a whisper so ancient it predates the formation of almost everything we see in the night sky. What other primordial secrets are encoded in that faint, uncharted portion of the glow? This perfect smoothness is actually an illusion. Behind the uniform glow of the X-ray background lie subtle, statistical ripples, tiny anisotropies that hold the blueprint for how its sources are arranged across the cosmos. Finding these faint patterns is like trying to hear a whispered conversation in a roaring stadium. You cannot pick out individual words, but by analyzing the statistical properties of the noise itself, you can detect the cadence and rhythm of the hidden voices. This is the same powerful technique used to decode the cosmic microwave background, the afterglow of the Big Bang. In that case, the minute temperature fluctuations, those tiny hot and cold spots, were the seeds that gravity would later amplify into the vast cosmic web of galaxies and clusters we see today. For the X-ray background, the principle is identical, but the target is different. The anisotropies we search for are not variations in temperature, but incredibly slight fluctuations in the number of X-ray photons arriving from different directions. A tiny excess of photons from one patch of sky, a slight deficit from another, these minuscule imbalances are not random, they are the direct imprint of the clustering of the sources creating the glow. If the dominant sources, like all those hidden black holes, tend to cluster together in space, then their combined light will create a correspondingly clumpy pattern in the background. By measuring the typical angular size of these faint clumpings, astronomers can work backwards to determine the typical physical separation of the sources billions of years ago. It is a cosmic ruler etched into the fog itself. A detection of strong anisotropies on large scales would tell us that the obscured black holes lived in massive, clustered environments, much like the galaxy clusters of today. A smoother signal with finer-grained ripples might point to a different, more uniformly distributed population. Each possible pattern is a fingerprint, and matching it to the right suspect is the key to finally understanding the architecture of the violent, high-energy universe. What hidden structures are these faint ripples trying to trace for us in the darkness, deep within the smooth, statistical fog of the X-ray background? Astronomers are hunting for a signal that would rewrite the laws of physics. They are searching for the ghostly fingerprint of dark matter itself. This elusive substance, which makes up about 85% of all matter in the universe, has so far revealed itself only through its gravitational pull. We cannot see it, touch it, or interact with it through normal means, but what if, under certain extraordinary conditions, it could betray its presence with a faint, high-energy whisper? This leads us to one of the most speculative and thrilling mysteries of the cosmic X-ray background. The theory hinges on a hypothetical particle known as the sterile neutrino. Unlike the ordinary neutrinos that stream through our bodies by the trillions every second, sterile neutrinos would be far heavier and, as the name implies, utterly aloof. They would interact with normal matter only through gravity, making them a perfect candidate for dark matter, and here is the critical part. Some theories suggest these sterile neutrinos are not entirely stable. They could, on very rare occasions, spontaneously decay. When one of these particles decays, it would transform into an ordinary, lighter neutrino and emit a single, specific X-ray photon. The energy of that photon would be like a unique barcode, determined precisely by the mass of the sterile neutrino. If trillions upon trillions of these dark matter particles are decaying across the universe, their combined emission would create a faint, monochromatic line hidden within the broad, messy spectrum of the X-ray background. It would be a single, pure note in the cosmic symphony. The hunt, therefore, is not for a broad glow, but for an impossibly faint spike at one exact energy. Astronomers have scoured the data from observatories like XMM Newton and Chandra, looking for any sign of this telltale line. There have been tantalizing, unconfirmed hints, like a faint spike detected from the Perseus galaxy cluster that matched the predicted energy for a sterile neutrino with a mass of about 7 kilo-electronvolts. But these signals remain controversial and have not been consistently seen elsewhere. The challenge is monumental. This predicted line is so incredibly faint that it is buried beneath the roaring signal from all the black holes, galaxy clusters, and other violent sources. Isolating it is like trying to pick out the sound of a single, specific pin dropping in the middle of a thunderstorm, yet the potential reward is beyond calculation. Confirming such a signal would not just solve a piece of the X-ray background puzzle, it would crack open the mystery of dark matter, identifying its fundamental particle after decades of searching. It would mean that the faint, ancient glow we have been studying for 60 years contains not just the history of cosmic violence, but the secret signature of the universe's hidden mass. What if the answer to our greatest cosmological question has been shining softly in X-ray light all along, just waiting for us to learn how to see it? A new eye in the heavens has just delivered a map that is rewriting our entire understanding of the X-ray universe. The E-Reseda telescope, a German-Russian instrument launched in 2019, has completed something no other observatory has ever managed. It has performed a full sky survey in the specific mid-energy X-ray band that is most sensitive to the elusive warmth of the cosmic web. For decades, the warm-hot intergalactic medium was a theoretical phantom, its signal buried in the noise. But E-Reseda's unprecedented sensitivity and its all-sky view have changed the game entirely. Its new map of the entire X-ray sky is not just an incremental improvement. It is a revelation showing millions of previously unknown sources and, crucially, capturing the faint, diffuse glow between them with a clarity we have never before possessed. This is like turning on a high-definition light in a room we have only ever explored with a flickering candle. The mission's first full data release has already provided the most accurate measurement of the cosmic X-ray background spectrum to date, and it is allowing scientists to perform a new kind of cosmic subtraction. By meticulously removing the light from every single point source E-Reseda can detect, astronomers are left with a cleaner, sharper view of the truly diffuse component than has ever been possible. They are peeling back the layers of the onion, one by one, to see what remains at the very core, and what they are finding is extraordinary. The data shows tantalizing, large-scale structures in the unresolved glow, faint tendrils and bubbles of emission that align perfectly with the predicted distribution of the missing baryons in the cosmic web. This is no longer just a hopeful theory. We are now looking at the first potential image of the universe's hidden skeleton, the ghostly architecture of the warm-hot intergalactic medium itself, slowly coming into focus. With this new map in hand, we stand on the brink of solving two of cosmology's greatest puzzles at once, finally weighing the missing atoms of creation and understanding the true source of the universe's oldest, most persistent light. What other invisible structures, hidden for billions of years, will we trace onto this magnificent new chart of the high-energy sky? Our own galaxy adds its own brilliant signature to this cosmic canvas, a local veil of high-energy light that astronomers must carefully peel back. The Milky Way is not just a collection of stars, it is enveloped in a colossal, invisible atmosphere of superheated gas, a galactic halo that stretches for hundreds of thousands of light years. This halo is not a uniform shroud, it is a dynamic structure sculpted by the violent history of our galaxy's central black hole. The most dramatic evidence for this are the Fermi bubbles, two gigantic orbs of energy that balloon out from the galactic center above and below the plane of the Milky Way. Each bubble is tens of thousands of light years across, and they glow faintly in gamma rays and X-rays. They are thought to be the ancient remnants of a past feeding frenzy by Sagittarius, a star, our own supermassive black hole, a titanic eruption that occurred millions of years ago and blew these colossal bubbles into the galactic halo. Beyond these giant structures, the entire halo itself seethes at temperatures of millions of degrees, emitting a soft, diffuse X-ray glow. This presents a monumental challenge for cosmologists. How do you separate the local light of your own galactic neighborhood from the faint, cosmological signal coming from billions of light years away? The X-ray emission from the Milky Way's hot halo is a foreground fog, and it lies directly between us and the true cosmic background. To see the distant universe, scientists must create incredibly detailed models of this local emission. They map the distribution and temperature of the hot gas in our halo, they account for the Fermi bubbles, and they even model the X-rays from our local solar system's interaction with the interstellar wind. Only then can they perform a precise cosmic subtraction, digitally removing the brilliant foreground to reveal the faint, ancient whisper from beyond our galaxy. This meticulous process reveals a profound truth. To understand the most distant reaches of the cosmos, we must first master the intricate details of our own celestial home. What other secrets about the universe's structure are hidden not in the distant depths, but in the faint, hot breath of our own Milky Way? Even the solar wind can cast an X-ray shadow. A strange and subtle process known as charge exchange adds a final layer of local complexity to our cosmic detective story. This phenomenon occurs in the seemingly empty frontiers of our own solar system, where the sun's constant outflow of charged particles, the solar wind, collides with the sparse gas of the local interstellar medium. In these quiet borderlands, a bizarre atomic theft takes place. A highly charged ion from the solar wind, hungry for an electron, steals one from a neutral atom of interstellar hydrogen or helium it happens to pass. The stolen electron doesn't settle gently into its new home. It drops into a lower energy state around the ion, and in doing so, it must release a packet of energy. That energy emerges as a soft X-ray photon. This is not the violent, million-degree glow of a black hole's accretion disk. It is a gentler, more specific kind of light, born from a simple act of atomic piracy. The challenge for astronomers is that this charge exchange emission is happening right on our cosmic doorstep. It creates a faint, shifting veil of soft X-rays that perfectly mimics the kind of signal we might expect from the warm, hot intergalactic medium, the very signature of the universe's missing atoms. This means that a portion of the diffuse X-ray background we painstakingly measure might not be cosmological at all. It could be the ghostly reflection of our solar system's own interaction with the galaxy, a local mirage obscuring the distant truth. How do we distinguish the whisper of the cosmic web from the faint sigh of our own celestial neighborhood? Even our most powerful observatories are blind to certain cosmic truths. They operate within strict limits, technological boundaries that define what we can see and what remains forever hidden in the X-ray fog. Our current telescopes, like Chandra and XMM Newton, are engineering marvels, yet they are constrained by three fundamental challenges. First is their limited energy range. They are tuned to see a specific window of X-ray light, but the universe emits a much broader spectrum. The faintest, most distant whispers from the first black holes are redshifted into an extremely low energy band that our instruments struggle to detect, like trying to hear a deep bass note with a radio that only picks up high pitches. Second is angular resolution. While Chandra's vision is phenomenally sharp, it still has a limit. It can resolve millions of sources, but what about the billions of fainter ones huddled just beyond that threshold? Their light blurs together into that stubborn, unresolved glow, a sea of anonymous points we cannot yet count or identify. The final, and perhaps most crucial, limitation is collecting area. Think of a telescope's mirror as a net for catching photons. Our current nets are simply too small to gather enough of the faintest X-ray light in a reasonable amount of time. To study the diffuse emission from the warm, hot intergalactic medium, for instance, we would need to collect X-rays from a single patch of sky for not just weeks, but for years or even decades. It is a task that is practically impossible with the tools we have today. These are not mere technical shortcomings, they are the locked doors blocking our path to the universe's deepest secrets. But a new key is being forged. The Advanced Telescope for High-Energy Astrophysics, or Athena, is a next-generation observatory designed from the ground up to shatter these barriers. Scheduled for launch in the mid-2030s, Athena will have a collecting area more than 10 times larger than any current X-ray telescope. This is the difference between catching rain in a teacup and using a swimming pool. It will gather photons with such incredible efficiency that it will map the faint X-ray glow of the cosmic web in just a few hours, a task that would take current telescopes centuries. Its energy resolution will be so fine that it can isolate the specific spectral fingerprints of different elements in the hot intergalactic gas, allowing us to literally take a chemical census of the missing baryons. And its combination of wide field of view and sharp vision will finally break down the unresolved background, revealing the faintest active galaxies and stellar remnants that have eluded us for decades. With Athena, the cosmic X-ray background will not be a fog to be studied, but a landscape to be explored, its every hill and valley laid bare. What long-hidden inhabitants of the high-energy universe will we find staring back at us when we finally open this new window? This faint X-ray fog is not a solitary entity. It exists in a crowded cosmos, surrounded by the light of its neighbors. To truly understand its secrets, we must listen to the entire cosmic symphony at once. One of the most powerful techniques in this quest is cross-correlation, a method that finds the hidden connections between different kinds of light. Imagine you are at a massive, noisy party trying to find your friend. You cannot hear their individual voice over the roar of the crowd, but you know they have a distinct laugh. If you hear that laugh from across the room, even if you cannot see them, you know exactly where they are. Cross-correlation does exactly this for the universe. Astronomers take the incredibly detailed map of the X-ray background and lay it over a map of the sky in a completely different wavelength, like the deep infrared view from the James Webb Space Telescope or the future radio sky from the Square Kilometre Array. They then search for places where the faint X-ray glow is just a little bit brighter in spots that also glow in infrared or radio. This statistical echo is a revelation. It tells us what these invisible, unresolved X-ray sources actually are, even when our X-ray telescopes are too weak to see them directly. A strong correlation with infrared light, for instance, is a telltale signature. It points directly to those heavily obscured active galactic nuclei, the hidden black holes shrouded in thick dust. The dust blocks the X-rays but absorbs the black hole's energy and re-radiates it as heat, glowing brightly in the infrared. So if a patch of unresolved X-ray fog consistently brightens in the same spot as an infrared glow, we have found our hidden monster. A correlation with radio waves might indicate galaxies with powerful jets, where the X-rays come from the base of the jet and the radio emission from its vast, extended lobes. Each wavelength correlation is like a new filter applied to a blurred photograph, slowly bringing the hidden image into focus. We are no longer just staring at the X-ray fog. We are asking it what it looks like in other colors, and in its silent answers, we are finally learning the true identity of the universe's faintest, most numerous violent inhabitants. What other invisible communities will we uncover by listening to the harmonies between different kinds of light? The faint glow of the cosmic X-ray background is the ultimate cosmic exam, a single, all-sky answer sheet for which we must invent the questions. To crack this exam, theorists have built entire universes from scratch inside the world's most powerful supercomputers. This is the monumental challenge of theoretical modeling, a digital laboratory where our understanding of cosmic evolution is constantly put to the test. The process begins with the fundamental laws of physics and the initial conditions of the Big Bang. Scientists program these rules into a virtual cosmos, then set the simulation in motion, watching as gravity works over billions of years of virtual time to form a cosmic web of dark matter. Onto this digital skeleton, they paint the normal matter, the gas that will collapse to form galaxies and the supermassive black holes that will seed their hearts. They assign these virtual black holes feeding rules, dictating how they grow, how they blow out gas in powerful winds, and how they eventually shut down. They model the obscuring donuts of dust and gas that can hide them from view. Once this synthetic universe is fully populated and its history written, the scientists perform a remarkable trick. They place a virtual telescope at a random point in their digital cosmos and command it to look out in every direction. They calculate the X-ray light from every single one of their millions of virtual active galactic nuclei, from the hot gas in their galaxy clusters, and from the faint, warm filaments of their intergalactic medium. They add it all up, and they generate their own version of the cosmic X-ray background. Then comes the moment of truth. They hold their synthetic sky up against the real one measured by Chandra and Irisita. Do the patterns match? Is the total intensity correct? Does the simulated background have the same subtle ripples, the same balance between hard and soft X-rays? More often than not, the answer is no. The first attempts are always wrong. The simulated glow might be too bright, meaning the virtual black holes are feeding too voraciously. Or it might be too smooth, meaning they haven't properly captured how these objects cluster together. Each mismatch is not a failure, but a crucial clue. It forces them to go back and tweak the underlying physics. Perhaps black hole feedback needs to be more efficient at shutting down accretion. Maybe the seeds of the first black holes formed differently. The model is refined, the simulation is run again, and the comparison is repeated. This cycle of prediction and revision is how we slowly, painstakingly, close in on reality. These digital universes are our proving grounds, allowing us to test ideas that would be impossible to observe directly. They transform the X-ray background from a static fog into a dynamic story, a narrative we can play forward and backward in time until the virtual sky finally, miraculously, looks just like our own. This faint high-energy whisper is not a permanent feature of the cosmos. Its future is written in the same expansion that stretches its light, a slow and inevitable fading into the cold, dark future. As the universe continues its relentless acceleration, driven by the mysterious force of dark energy, the very sources of the X-ray background are being systematically shut down. The great age of black hole feasting is already behind us. Cosmic noon has passed, and the universe is settling into a quiet, geriatric era. One by one, the brilliant active galactic nuclei are dimming as their fuel supply is exhausted or blown away. The galaxy clusters, those colossal knots of hot gas, will slowly cool, their fierce X-ray glow softening over billions of years. The stellar endpoints, the neutron stars and black holes in binary systems, will eventually consume their companions or spiral together and merge, falling silent. The universe is running out of the violence needed to power its high-energy sky. The background will not vanish overnight, but it will undergo a profound transformation. The hard, piercing X-rays from obscured black holes will be the first to dwindle, as those shrouded monsters are the last to run out of gas. The softer glows from clusters and the warm, hot intergalactic medium will persist longer, but even they will cool and fade as the cosmic web is stretched ever thinner, its density dropping to near nothing. In the far, far future, the X-ray background will not be a roar or even a whisper. It will become a ghost of a ghost, a faint, uniform microwave hiss that is utterly indistinguishable from the cosmic microwave background, the cooled remnant of the Big Bang itself. The two great backgrounds of the universe, one from its fiery birth and one from its violent middle age, will finally merge into a single, cold, and silent echo. Yet, even in this final state, the story may not be over. Could new, unforeseen phenomena emerge in the cold, dark eons to come, perhaps the slow, quantum evaporation of black holes via Hawking radiation will produce a final, faint flicker of high-energy particles. Or maybe the decay of dark matter, if it occurs, will become the dominant source of X-rays in a universe where all other lights have gone out. The ultimate fate of the cosmic X-ray background is inextricably linked to the fate of everything. Its slow fade is the cosmic equivalent of a final, dying breath, a signal that the era of structure, of growth, of violent and brilliant life has finally come to an end. What final, unimaginable chapter will be written after the last X-ray photon from an active galaxy has faded from the sky? From a single, baffling hiss in 1962, we have mapped an entire hidden universe. This journey through 25 interconnected mysteries reveals that the cosmic X-ray background is far more than a simple fog. It is a rich, layered archive, the ultimate record of the universe's most violent and transformative events. We have decoded the light from hidden black holes, felt the heat of the missing atoms in the cosmic web, and listened for the whispers of dark matter itself. Every photon in that glow is a page in a cosmic history book, telling the story of how monsters grew, how galaxies were forged, and how the raw material of creation was scattered across the voids. The case is far from closed. With every new map from Rosetta and every future observation from telescopes like Athena, we will peel back another layer, solving old puzzles and undoubtedly uncovering new ones. The universe is still speaking to us in this high-energy language. Stay curious, follow these incredible discoveries as they happen, and let us know which of these cosmic mysteries captures your imagination the most. What secret of the universe do you hope we decipher next?